he did his graduate work here at Davis and completed it in 1976, I think. 70. It must have been later than that. About 1980. His thesis project was the evaluation of the shear profile near the bed of a cohesive tidal channel. And it was a bed that was very soft. And our concern was whether the interaction with the bed altered the shear profile near the bed. And it turned out that it did at near times of slack water, but not otherwise. So you had uniform shear, and the logarithmic velocity profile prevails near the bed in an area of rapid deposition. He then, after graduation, went to work for the Corps of Engineers at the Hydrologic Engineering Center. And he was there for some years, and during that time, he was voted Man of the Year for the entire Corps of Engineers nationwide. Yeah. So he's a pretty confident person. He engaged in training activities with the Hydrologic Engineering Center during that time, and worked on mud flows in Utah and Oregon. That's why he talked on mud flows, right? Yeah. And worked with a number of other people. He left about 3 or 4 years ago and worked for a company in Colorado, Simon Lee and Associates, on general river problems. Then in 1989, he came back and worked for the Corps for a time, and now he has the branch of water engineering and technology here in Davis. So he's in private practice. We're good friends, and it was awful nice of him to come take my place while I was gone.
He also talked about the Oakland fire and the impact the fires had on the soil and the change in the structure of the soil.
In Oakland?
Yeah.
Yeah.
And the implications for infiltration of rain and what that might do for erosion.
Mm-hmm. He's working on that problem now. It's something he's very much involved in. He worked on the breakwater at Fisherman's Wharf. I don't know if you're familiar with it. There's a new long breakwater there. It was built about 3 years ago by the Corps of Engineers, and he was the primary principal responsible for the design of that facility, including all the impacts on water quality that it would have, and the construction problems. It was quite a project. Well, let's see. Last hour, we were talking about mixing some.
Where are we supposed to meet for the field trip on Saturday?
Oh, good point. Thanks. 8 o'clock in the parking lot right here by the silo at this end of this parking lot. You all are familiar with this area here. We should be back mid-afternoon. Come warmly dressed, because we'll be out in areas where we might be exposed to wind, and wear old shoes. We can either take our lunches and eat them on Marina Green, or we can stop at a restaurant. What's your pleasure? Anyone have any preference?
I prefer the less expensive route.
Anyone else? You want to take a lunch? Okay, let's all bring our lunches then. And it's nice to sit outside, but it might be a little breezy, so bring warm clothing. It's often cool in the Marina Green. Any other business before we start? Okay, last time we met, we were discussing mixing zones of estuaries. And what I'd like to do this morning is to show you some data from a mixing zone in an estuary that illustrate the problems better, I think, than any drawing on the blackboard that I can do. So what I'll do is describe the study and the measurements that were made and show you what the measurements showed, describe what the measurements showed, and point out the processes that go on in an estuary. It's a rather complicated system, but I think by looking at it piece by piece, the components will become clear. So let's put on the slides and look at the real data. Thanks, John. Well, the estuary I thought I had a plot of the estuary. Well, the estuary is the Savannah estuary in Georgia, and it sooner or later I'll find the plot of it. It consists of a river mouth that goes out to the sea, and there's a branch, a back branch, bifurcation, and a back branch that's shallow that also goes out to sea. It joins the original one, so there's a big island in there. We looked at the deepened part next to the city, which is an almost uniform channel, 30-some feet deep, and one that's maintained by dredging. It's in a mixing zone, and the deposition rate there is very rapid. That's the reason we selected it. Because the deposition rate is rapid, the material on the bottom is very soft, like the material we saw in that jar that I showed you. We needed to know the velocities and suspended solids concentrations and salinities as a function of distance above the bed in order to describe the shear stresses on the bed and the character of the flow accurately. So we had to sense the surface of the bed somehow. This device was created to do that, and it consists of an inner hoop that you can see here with 3 vanes on it. So in plan view, it looked like this with 3, and there was a tube here. Side view looks like this, with the tube in the center and the vanes out to the side. This, and on this, at the upper of these inner vanes, were 3 cylinders that were filled with L. So the gravity force on this cylinder was just slightly greater than neutral buoyancy. That is, it would weigh it down. And it was adjusted so that when the shear stress on the wall of the hoop and the vanes on the inside was about 1 dyne per square centimeter, it would support that device. You follow me? So what it would do when the surface of the mud was reached, it would settle into the mud to the point where the shear strength of the mud was sufficient to support it. The inner cylinder here, the tube, rode on another tube with a bottom on it. So this tube might look something like this here, and it had a length about twice the height of the tube. And inside of this tube was a magnetic reed switch, which is just a little switch that has flexible magnetized contacts, so that when a magnet came by it, the contacts joined. And on the vanes were 3 little ceramic magnets, like this. So that when the mud surface was reached, the veins would stay still, and if you lowered its support a little bit, then the magnetic reed switch would slide in between these magnets and close that switch. That operated a small audio oscillator connected to earphones of the operator above, so that as he lowered it to the bed, when the tone started, that was the bed surface. We compared it with pedometer measurements, that is echo sounding measurements, made at high sensitivity so we could detect the surface of that soft mud, and it compared very well. So it provided a means of sensing the surface. Above that, just above that device, was was a current meter, just an ordinary Gurley current meter, that provided an indication to the operator of the velocity, and a compass that showed the direction of the current meter. The vanes on this weight and on the current meter directed the Gurley meter toward the direction of current and indicated its direction up above. There was a lucite plate fastened also to the string, and the purpose of the plate was to keep it from bobbing up and down because of surface waves. And the support for the string had an elastic arrangement so that it would give with the fluctuations of the boat. The procedure was to lower this down until and incidentally this was 1 foot, lower this down until the operator sensed the surface of the mud, then take a current reading, direction and velocity reading. I neglected one thing. Not shown here is a 3/8 inch diameter tube whose end was right behind the current meter, and that was pumped continuously. And after a couple of volumes of the fluid displaced the water in the tube, a sample was taken with its temperature read and salinity, and later suspended solids determined. So we had measurements of suspended solids, salinity, and temperature, and current all at the same elevation. After making that measurement, which took just a couple of minutes, the apparatus was raised a known distance. We had a calibration on the reel so that we could raise it to 2 feet, 4 feet, 8 feet, 16 feet, and so on, and make similar measurements at those elevations. So it provided a means of getting a profile of all those parameters. I'll show you some of the results now, plotted on the same plot. The top is currents, and the axis is this axis is flooding in this direction and ebbing in this direction. That is, flowing toward the sea in this direction, flowing toward the land in this direction. And the solid squares are the 1 foot that is measured 1 foot above the bottom of the estuary. And notice here that the currents, the solid squares during flood follow this pattern during flood, and then during ebb they follow this pattern. So that during ebb the velocity was very much less than it was during flood, and the duration was very much longer during flood than it was during ebb. You follow me? If you contrast that with the surface, say, well, let's take the 25 foot, which is a round solid dot. Well, let's take the surface. The surface, you can see, has a very much shorter time than it does during ebb, and the velocities are very much greater during ebb at the surface. So we have opposite conditions, surface and bottom. The ebbing at the surface occurs, or I'm sorry, flood at the surface occurs in a relatively short time compared to ebb. And the amplitude, and at the bottom, let's say, the flooding occurs a long time relative to ebb, and the amplitudes are opposite. That is, the amplitude of flooding on the bottom is very much more than the amplitude of ebb near the bottom, and conversely, the amplitude at the surface of flood is very much less than its amplitude during ebb. So we have a situation where at the bottom, during this period, water is flowing during this period, water is flowing downstream on the surface and flowing upstream on the bottom. And in fact, it's flowing upstream on the bottom for all of these things up to 16 feet. So there's a lot of water moving upstream on the bottom during that period. And that's more than an hour. That's about an hour and a quarter, say. So, and then similarly, here you can see that it's a little more spread out here than it was. Slack water occurs at different times on the surface and on the bottom. That's what that tells us. Now, at the same time, during flood, the suspended solids concentrations, even 1 foot above the bottom, were low until the near bed velocities were high enough to suspend material. Then it increased suddenly, and it stayed fairly high for a good portion of the flood period near the bottom, then was near zero during most of the ebb period. So we have a kind of a rectification. The material was suspended during flood on the bottom as the bottom currents were moving landward, but they were not suspended during the period that water was flowing seaward. So there's a net transport upstream, a rectification, if you like, of the transport upstream. Keep in mind that the shear stresses on the bed is proportional to the square of the current. So a small change in current can have a significant impact. And while that doesn't look like much of a difference, you can see that when the currents were on the order of 1 foot per second or less, that there wasn't any suspended material on the bottom. Another interesting feature, you'll see more of this later, is that the material near the bed, well, this is the 4 foot elevation, and this open one is 8 foot elevation. The material from 8 feet downward deposited in a very short period of time. The settling velocity must be really appreciable for it to settle that fast and stay settled. This is at the most seaward station during a mean tide. Now, I'd better say something about this. If this is the ocean, we had 3 stations, and this is landward. Three stations that were in the mixing zone. The mixing zone actually extended beyond these 3 stations to some extent. The figure I showed you here is the most seaward of the stations, and the tide is a mean tide. Notice that the salinities changed. First of all, there's quite a difference in salinity top to bottom. At the lower elevations, it's a maximum, and at the surface elevation, it's about a third of that. This is 10 parts per thousand, so it was about 14 parts per thousand at a peak. And it varied from about 7 parts per thousand to about 14 parts per thousand in that region. So you can see we're still in the mixing zone. Seawater salinity is about 34 parts per thousand, 33 or 34. So it was quite saline, and there's quite a difference in salinity from the bottom to the top. These are logarithmically spaced, so you need to keep in mind that there's more space between these than there was between these at vertical elevation. Well, that's the most seaward one. Now let's take a look at the next most landward. What's that?
What do you think is going on at it's like hour 19 and a half where it drops, where all the points tend to drop down in the middle chart?
This dip here?
Yeah.
I don't know what the reason for that is. There doesn't appear to be. Well, there is a little dip in the currents here. I don't have any explanation for that. Now the next most landward station looks like this. You can see we still have the same kind of current distribution that we had before, with a shorter difference in time between the surface and bottom, but the same conditions prevail. That is, at the bottom we have a longer duration of flood flow than we have during ebb, and at the surface we have a much shorter flood period than we have ebb, and the amplitudes are like those that we saw before. Notice that the rectification that we saw isn't quite as complete as it was before, but the concentrations are higher. That is, during the strength of flood on the bottom, the concentration near the bed rose appreciably, and then during ebb it only rose during one of the sampling at 20 minutes interval. But the bias is still there. That is, there's much more material transported during flood flow than during ebb flow. So the movement is upstream on the bottom. The salinities are lower than a little, and they fluctuate about the same as they did in the past. Notice, however, that there's still quite a difference in salinities between the bottom and the top. This is the middle station now at a mean tide. This is the most landward station during the mean tide, and you can see that the surface currents now aren't quite as, they're still strongly biased, but not quite as biased as they were before. The near bed velocity is still stronger than during flood than it is during ebb, although not much. You notice this portion here, it's almost as strong as it was during this portion, in the opposite direction, of course. And notice the corresponding suspended solids concentration. This went up to 2549 parts per million, 2 grams per liter during the strength of flood, with fluctuations in it. And then during this, when this increased, there was an increase in near bed suspended solids. Still, the net transport is upstream. That is, there is more transport upstream than there is downstream, but the downstream is beginning to beginning to transport, I should say, material is beginning to be transported downstream in significant amount. The salinities, you can see, are quite a bit lower, and during this portion, they're the river salinities. Only near the end of flood does the salinity rise to a higher value. So we have a water mass. You see that there's a net movement this way as well as the shearing going on inside it. Okay, that's the most landward station under a mean tide. I'll show you the conditions under another tide. For some reason. The slide doesn't want to go down. This is a neap tide. Remember, when the tides are about the same, the diurnal tides are about the same, we call it a neap tide. So that's the least of the tides. And you can see that everything is weaker than it was before. The amplitude of the flood and ebb are weaker, slightly weaker, and that the duration of the flood tide near the bed is longer than it was before. The whole system is more nearly a stratified system. And you can see that the duration of ebb near the bottom is short, and the amplitudes, or the amount of material put in suspension, is less. In other words, with a neap tide, there's less movement back and forth, so there's less shear stress on the bed and less material put in suspension. We get strong upstream, that is, most of the movement is in the upstream direction compared to the downstream direction. And the salinities don't change very much. This should be the middle station. Salinities don't change. So we have a system that's apparently more stratified. There seems to be a difference right in this 16-foot elevation in the bed. But otherwise, it doesn't change very much. That is just a weaker tide system. Most landward station oops, that's the spring tide. I guess I missed the neap tide. A spring tide is the tide with the greatest range. Remember when you have something like this, it's a spring tide, where you have the greatest range from top to bottom. And you can see that the activity is much greater. This is the most seaward station. The amplitude of the flows are much greater. The bias is still about the same. The amplitude of the amount of suspended solids put in suspension are very much higher. I don't see it goes way up. It doesn't say what it is. But there's also a significant amount of material put in suspension during the ebb tide near the bottom. The change in salinity percentage-wise is more marked than it was before also. This is river salinity. Now this is the most seaward station. This is the middle station. And you can see that there's more mixing going on up above there in the currents, but the biases are still there. If you look at the near bed plot, it's very much longer in time than during flood than it is during ebb. The suspended solids concentrations were very high during flood, less high during ebb. So there's still a net movement upstream. The salinities varied from just above river salinity to about 10 parts per thousand in this middle station. So there's much more activity when the tides are stronger and the water motion is more pronounced. And this is the most landward one. And you can see now there's less bias. The amplitude of the flood near the bottom is about the same as the amplitude during ebb, and the duration of upstream flow on the bottom and downstream flow on the top simultaneously is still about an hour and a half, maybe hour and a quarter. Lots of activity, but activity in both directions. Now, if we had a station further up, what you'd find is that these would be about the same. Just move back and it would move back and forth. Salinities again are very low in the landward station and only above river salinity during the.
So this is still seaward of the null zone.
This is landward end of the null. Oh, the null zone is right about here. This is about the.
Very close, but
What's that?
that's close, but not quite to the null zone.
See, if these were the same, they're not far from the same. This would be the null zone. So the material is just moving back and forth in that area and accumulating, as I'll show you. And you can see that about something like half the time, or maybe a little more than half the time, you have river salinity. So we're right at about the null zone in this most landward station. Ebb predominance is really the ratio of the distance material moves downstream, some of the upstream end. But these three stations is the most station and one is the most landward station. So at the most station we have flood predominance in this direction. Flood predominance about 18 from the bed up to about 18 feet, and strong ebb predominance above that, in the water above that elevation. Contrast that with this most station during a mean tide. Most land, you can see a flood predominance from about 7 feet to the bed. And all above that is ebb. Now, keep that picture in mind. The range, and you can see together than they were in the previous one because of the greater mixing. And notice particularly that the most landward most predominance from about 8 feet down. In other words, that's about the null zone. That's the point where ebb and flood predominance are about the same.
So with a stronger tide, then the null zone moves seaward?
Say it again.
This is under the spring tide?
This is spring tide. This is the last set we looked at.
So it's a very strong.
It's a strong spring. There's strong mixing because there's lots of flow back and forth.
Okay. And that brings the null zone seaward.
It brings it seaward, a little bit seaward. See, under a neap tide, the stratification is more nearly complete, so it has a flatter slope to it. Under a spring tide with more mixing, it has a steeper slope to it, so it brings it quite a pronounced steeper slope. And this is the neap tide condition. You can see it's the elevations of the 50% ebb predominance are higher, and there's more flood predominance near the bed than during spring tide. Just what I was describing. Now this is a plot just for orientation. It's a plot of a logarithmic velocity profile, current in feet per second on the bottom, and elevation above the bed. And it's for velocities of 1 foot per second, 2 feet per second, and 3 feet per second, calculated according to the logarithmic velocity profile. And A is the slope of it, 0.176 up to 0.491. These are just calculated, and the purpose of showing this to you is so that you'll have some basis for comparing what's observed in the estuary. This is the salinity profiles at the most seaward station during a mean tide. You can see that the salinity is lower near the surface and increases near the bed, and it's about the same from about 6 feet down, or maybe 8 feet down to the bed. These are for different times, successive times, so that you can see it changes with time, but the slope is about the same. This is at the middle station during a mean tide, during flood, I should point out. And it looks the same, except it's all moved to the left a little bit. The salinities are lower, and from about 8 feet down, it's nearly constant. This is a mean tide at the most landward station. Same kind of a profile, except the concentrations are all lower than they were before. This is flood current profiles, and current profiles during a mean tide. And you can see that there's a lot of bias near the top. That is, it's during flood, even during flood at the top, I should point out, there's a bias downstream at the top. Up below about 8 feet, it looks something like a logarithmic velocity profile. The ordinate is a logarithmic scale, and the abscissa is a linear scale. This is the middle station during a mean tide, and that same kind of bias prevails. The slope is a little bit steeper than the slopes I showed you earlier for that velocity profile. Remember this is about 1 foot per second. These look like this, and the 1 foot per second looked something like this. So it's more, the velocity is more spread out, more like a laminar profile than it is a turbulent one. Turbulent profile would definitely be steeper than that. I'll show you some more figures. This is the flood current during a mean tide at the most landward station. And there's some lines drawn through there. It looks like a semi-log, a logarithmic velocity profile, but the values of A for those low current are much higher. Now this is the ebb current profiles. Those were all floods. Those are ebb current profiles at the most seaward station during a mean tide. And notice that near the bottom we have what looks like a normal logarithmic velocity profile up to about 5 feet, and then above that it's very much flatter. This contrasts quite a lot with what you'd expect for uniform density. And that, as I showed you earlier, the density profiles, or salinity profiles, I should say, look something like this. Now this is a logarithmic scale. It spreads out this dimension here compared to higher values. But in the region where the salinity is nearly uniform, we get the normal logarithmic velocity profile. But where the salinity is changing, in this region of change, we get this very much flatter profile. And the reason is that momentum transfer upward from the near bed region is inhibited by the density gradient. That is, when turbulent mixing tries to mix material upward, that mixing is inhibited by the fact that the material above has a lower density than the material below. And the result is you get this almost laminar velocity profile above that. Now that's from 5 feet up, so the top 30 feet or so of water depth has this very strong velocity gradient in it. This is the middle station. Same thing prevails, except that the uniformly dense, or the velocity profile for uniformly dense material is thinner than it was during the preceding one, but we still have that strong velocity gradient above now about 2.5 feet. And here's the most landward station, and it shows it for a succession of times. Remember, at the landward station there was part of the time we had river water salinity, and then part of the time we had increasing. So when it was river water, we had a normal velocity profile, uniformly dense water over the profile. Then as the saline water moved in, we had continuously changing profile to the flatter one, as shown before. These are calculated velocity gradients, and I'm not happy with that calculation. It assumes a simple relation between velocity gradient and internal shearing rate. But I think essentially in form it's probably not far off. The important thing about it is that for A equal 0.5, something like the uniformly dense material, the velocity profile shows, the gradient profile shows increasing gradients right near the bed, as you would expect, but then not much different toward the surface. Whereas for those flat velocity profiles that we saw, the velocity gradient is high throughout the profile. That is, from the bottom clear to the top. Remember, velocity gradient aggregation is the most important mechanism for causing interparticle collision. Now this is an attempt to put it all together. What we saw there was fairly low concentrations of suspended solids in the river water coming down. And from the flood data, particles were moving upstream during the strength of flood, deposited during the ebbing period, and then were resuspended during flood and deposited again and stayed there during ebbing period. But eventually, up here, they began to go back and forth, and at the null zone, at the point where the net movement upstream and downstream was zero, they were just going back and forth. These during the strength of flow, these particles mixed upward and mixed with the river water, incoming river-borne particles, which were dispersed. And the finer suspended aggregates mix upward more easily than the heavier ones because their settling velocity is less. So it provides a circumstance where we have we have aggregated particles mixing with unaggregated particles in a saline region, more than, say, 2 parts per thousand salinity, and with a high velocity gradient. So this whole region up here is ideal for the formation of aggregates, suspended aggregates. Particles that are carried back out settle out in the broad parts of the estuary where the velocities are very much lower and are carried back upstream again. So this is a loop, if you like, a continuing process of circulation. Well, river-borne material is brought in continually from upstream, and because the particles settle downstream and come back into the system, the loss to the ocean is less than the supply by the river. So we have essentially a sediment trap. Now, if the material stayed in suspension, as I showed here, eventually the concentrations would get higher and higher and higher. You know, they wouldn't reach some maximum value. But the reason that they don't exceed some maximum level is that each time that material deposits on the bottom, at least the lower portions of it consolidate and become stronger than the deposit, the remainder of the deposit. So that during the strength of flood, material on the bottom is resuspended down to the depth where its strength resists the applied shear stress. And because of that consolidation process, there's a net accumulation on the bed. If this area weren't dredged, the water would become shallower and shallower until the shear stress on the bottom, or until the cross-section, I should say, moved this mixing zone further out, you know, until the river mouth was further out, and it would just deposit until there was enough shear stress on the bottom during ebb to maintain the cross-section. And that's what a natural stream looks like. The problem is that here it was dredged, and consequently they have this mixing zone move upstream, and the shear stresses on the bed are insufficient to suspend that consolidated material. There it is. That's the one I wanted to show you first. That's the Savannah Estuary, and the location of the sites that I described were 130, 120, and 110. This is the city of Savannah, and this is dredged here. This is Front River. Back River is like a tidal slough, and they join back in this region. This goes back out like that. The sedimentation rate, the highest sedimentation occurred in this region here, partly because of the channel was widened for this mooring, a place where ships could rest while they were waiting for a berth on a pier. This estuary has been a serious problem for the Corps of Engineers for a long, long time, and they've tried various means of relieving it. What was finally done, and it was quite successful, I might add, is to deepen a region in Back River. I've forgotten the length of it now, but it was quite a long region. To deepen it and put a tide gate here. That is a large gate that opened during flood tide and closed during ebb tide. And what that did was to carry the suspended solids that moved back out this way, back up into this region during flood tide. That is, it was a pump, a tidal pump, if you like. The gates, it's just a gate that closes during ebb tide and opens during flood tide. So it created a net circulation in this direction in Back River. That caused them to accumulate in this deepened area edges because the cost of dredging this is very much less than the cost of dredging down here. The distance of transport is shorter, and you don't interfere with shipping while you're doing the dredging. So it seems to be pretty successful, but they still have to dredge. In 1974, one of your predecessors developed a mathematical model of sediment transport, and he verified it using the Savannah, and he calculated the concentration of sediment material regardless which station this was, what station, and it's shown on that in the dashed lines. Both the actual and this is an actual suspended sediment concentration as measured, and this is what the model showed. So you can see it didn't quite fit there, but in other cases it fit quite well. It did show the deposition during slack water, and most importantly, it showed that it yielded the sedimentation rates that were observed. And this is a profile, greatly exaggerated vertical dimension of deposit during a tidal cycle. Started out with a clean bed at the top, as an estuary, and then as slack water approached, material deposited as shown by that dark, thin layer up above. And as slack water, there was more deposited. Then on the bottom, at the beginning of strength of flow, it began to be resuspended. And more and more was resuspended, leaving material in the near the null zone. And these dimensions, by the way, came out to be about the dimensions that we observed with a fathometer. And you can see that there's more that has moved a little bit upstream, and there's more of it down there. Oh, that was the last of it. In any case, it showed deposits that looked very much like the actual deposits that we observed with the fathometer. Well, now I want to turn to another topic. I don't know if I'll be able to complete it before the hour's over, but let me at least start on it.
this model is to the vertical or horizontal?
It's a vertical,
That's what the average.
vertical two-dimensional. Wow. That's actually that model is used by the Corps of Engineers now nationwide. It's the TABS 2. It's been improved since that one, but it's essentially the TABS 2 model.
Yeah, but
It was Dr. Estuary's model. I'd like to describe the sediment distribution in the San Francisco Bay system. I think it illustrates a lot of points. First of all, it's the most complex of the estuaries I've looked at, and I've looked at many estuaries. It has a little bit of everything in it. Maybe not as high a suspended solids concentration as some others, or as high a tide range, but it has the phenomena that we're concerned with in it. This drainage to the San Francisco Bay system includes this entire 60,000 square mile drainage area. So that at one time, before the rivers were dammed, the drainage from that whole area, rainfall onto the valley floor and snow melt from the Sierras, flowed into the San Francisco Bay system. I might point out that the Sierra Nevada slope from the west edge to very near the eastern edge. Then there's a sharp escarpment on the eastern side. There are mountains that are tilting up this way. That is, they're still tilting. And their tilt is evidenced by the very steep V-shaped valleys for the rivers. If you're interested in the Sierras, you've probably noticed that. The river valleys they're not the usual mountains with a floodplain. There's very steep valleys like this, and they tend finger-like upslope. The east side of the Coast Range is dry. That is, it's very arid in the rain shadow of the Coast Ranges, but there are at times flood flows, as evidenced by the fans that flow out from those rivers. The main water flow, however, is from the north and from the face of the Sierra. Because of the climate, the rainfall occurred in the winter months, as I've described before, and the snow melt occurs in the spring months, up to about June. And so there were high flows into the bay system from the Central Valley drainage during those months, and they were, of course, episodic. Some years were much more than others. There are floods in record where it's claimed that you could row a boat from the foothills of the Sierra to the foothills of the Coast Ranges. And there's no doubt that occurred at times, because all the soils in the valley bottom are alluvial soils that have been brought down from the erosion of the hills. In any case, large amounts of water flowed originally in. That now is greatly curtailed by the water development projects, as I'll describe earlier. There's also local drainage into the bay system. The Santa Clara River, Stevens Creek, the Alameda Creek, and Petaluma River and Napa River provide relatively smaller amounts of water into the bay system. And their flows occur during rainy periods. That is, there's not much snow. Snow is rare in this region. So that we have a system with a water supply that's really episodic, that is wintertime supply. About 90% of the water comes in just a few months' time. And of course the sediment too. The hydraulics of the system are curious. First of all, note the interesting configuration. There's a very narrow opening at the Golden Gate. It's quite deep, but it's narrow compared to the cross-section of the bays downward. Another narrow section at Carquinez Straits, at Dunbarton Straits, the South Bay here. A constriction between Oakland and San Francisco. Another one between Point San Pedro and Point Richmond. And then Carquinez Straits, which is quite a constriction between San Pablo Bay and Suisun Bay. And then the delta channels altogether have a significant amount of surface area. So we have a system of broad, shallow bays interconnected by narrow openings. When the water surface of the ocean rises due to a rising tide, then water flows through the Golden Gate and causes the elevation of the water surface in Central Bay to rise. Andy?
Ray, where was Vallejo Bay?
Vallejo Bay was right there. I may have some other slides I can show you there. It was right there. And Southampton Bay was also. Southampton Bay. In fact, if you go there, you'll find the Southampton Estates now a development on where Southampton Bay used to be. And there's some old wooden ships buried in the mud in Southampton Bay, under the mud in Southampton Bay. And it, what's it? Water depth? 70% of these bays is less than 15 feet. Yeah, it's about 300 feet deep here, right in the narrow opening. It's quite deep in this narrow opening. It's about 100 feet deep right here. And there's a channel that runs down through here that's about 30 feet deep, if I remember correctly. A narrow channel. The rest of it's shallow mud flats. This is really quite shallow up here. There's a channel that runs across the southern part of the bay, but this is on the order of 6 feet average, over the water. It's quite shallow. And these bays are even shallower. Well, getting back to the tides, as the tide rises in the ocean, water flows through this narrow opening, causing the elevation of the water in Central Bay to rise, and water flows north and south as it rises, causing these water surface elevation in these outer bays to rise, and so on up through the system, with the result that there's quite a delay in the rise of tide in these upper bays. It's about 2 hours. That is, the tide rises in Suisun Bay about 2 hours later than it does at the Golden Gate. You follow me? And of course, the amplitude is reduced also. In addition to that, the resonance that I described earlier occurs in the South and Central Bay region, with the result that the amplitude of the tide in South Bay is about 2 feet greater than the amplitude of the tide at the Golden Gate. That is, the water surface there's a standing wave with the water surface going up and down. This standing wave, because of friction, is out of phase with the flow in and out of the Golden Gate, with the result that water flows past Treasure Island down into South Bay as the tide rises in South Bay, and then it flows back past Treasure Island into North Bay and San Pablo Bay during the opposite part of the tide, and then in between that, water moves in and out. So that the system is really mixed. That is, material from San Pablo Bay gets down clear into South Bay, and vice versa. During, one last word about tides, during historic high flows out of the Central Valley, the elevation of the tide has increased a foot or more in the Central and San Pablo Bay because of this higher tide and the restriction to flow caused by the Golden Gate and the straits between San Rafael and Richmond. During very high flows, the salinity gradient moves out, and in fact it extends way out into the ocean. I've seen turbid water on the surface way out close to the Farallone Island during flows on the order of 100,000 cubic feet per second out of the Sacramento River system. In any case, the combination of the resonance and the tides creates mixing and promotes transport of suspended materials throughout the system. Now, the sediments, suspended sediments that come out of the system, come largely down through the Sacramento River system, and less from the eastern streams and San Joaquin River now because they're dammed. That is, they're strongly dammed. The Sacramento River flow is also restricted by Oroville Dam and Shasta Dam And I might say that all these dams along the tributaries of the San Joaquin River and the eastern streams also restrict the flow that comes out. Still, during periods of rainfall, the water becomes less saline and the suspended solids become much greater during periods of high runoff. The salinities in these bays are sufficient to make the particles cohesive, and that combined with the fact that the velocities are low in these shallow areas facilitates deposition of that material that came in suspension. In fact, measurements out in San Pablo Bay have shown that as much as 2 feet of new material deposit at the end of the rainy season. During the remainder of the year, particularly the spring and summer months, the onshore breezes across these bays, which are primarily west to east, generates waves that suspends that material. And I invite you to watch the surface of the bay when you drive down that way, and you'll notice that during the spring and summer, the surface is brown, very turbid. Suspends those newly deposited particles and keeps them in suspension while these tidal currents that I mentioned circulates it throughout the system. Now, these breezes blow during late morning and most of the afternoon. Then the remainder of the day, the breezes die off and they're quiet, with the result that by midnight or so, the water's pretty clear. And because most of the bay is shallow, most of that material deposits in shallow areas. And it stays there until the currents are too low to suspend it. It stays there until the winds rise the next day and the material is put back in suspension and then continues to circulate. The result is that the material deposits and is suspended and circulated and deposits and so on repeatedly, and it enters this mixing system I talked about and moves back and forth, accumulating in areas where it's not, again, resuspended, including places like Oakland Inner Harbor and, deepened areas. The pulse that comes down, if you want to call it that, during a few months in the winter, arrives in South Bay about June. That is, the peak here is in, say, January, and the peak down here is about June. So there's quite a delay in this transport process. The material that the material that's left, I should point out that these local streams, Petaluma River, Napa River, and the streams that drain the east side of the Peninsula Mountains, Alameda Creek and so on, bring some sand into the system. And there's some fine sand brought in here. That mixes with the cohesive material, and it's left when the waves suspend the finer material. Finer material is carried off. It's a winnowing, like winnowing wheat. The finer particles are winnowed, with the result that the material arriving down here is finer, more clay, less silt, and less fine sand, if any, than the material that comes into San Pablo Bay. The sand makes the material, when the concentration of sand in the deposit is high enough, it makes it resistant to the waves. And the result is that after the new material is washed away, there's this little crust on the surface of San Pablo Bay that has fine sand in it, and wherever the wind is strong, you can go out there in waders and wade in. In my duck hunting years, I used to wade out in some of these areas, and as long as you were in an area that's swept by the wind, the bottom was firm and you could walk on it. If you stepped off into an area that was sheltered, however, you'd suddenly go down. There wouldn't be that support. Well, you're getting ahead of my story. Historically, these bays were considerably deeper, and I'll show you in just a minute. And in the 1860 to about 1877, there was a large industry of hydraulic mining in the Sierra Nevada, mining that was done by spraying very large streams of water against alluvial cliffs and washing the material down through riffles, they call them, through a little rectangular channel with bars across it, and gold would drop out behind the bars, and the gravel would be carried on through. Well, it produced huge quantities of gravel, In fact, the Yuba River has a deposit that's 3 miles wide and 40 feet deep of gravel between Marysville and, well, up to the foothills there. This huge amount of sand and gravel caught people's attention, and in fact it raised the elevation of the bed of the Sacramento River and caused flooding. And the consequence, I won't give you all the gory details, but the consequence of that was that the first environmental law passed in the state of California, as far as I know in the nation, was the law prohibiting the discharge of mining material into the river system. No one paid attention at that time to the fine materials in it, and huge quantities were in the bay system from the fine materials from the mining is about 1.9 billion cubic yards, a lot of material. And that material, Suisun Bay and quite a bit of San Pablo Bay and South Bay and Valle Bay, that material that came. Now there's only a chance by the strength of the currents in this through Carquinez Straits. The bays were just completely filled in. In 1914, well, prior to 1914, Geological Survey, a study of sedimentation in the central system. He published it in 1914. Quite a famous report and one worth reading. I mean, it's included studies of debris all the way down through the parts of that in San Francisco Bay. And he studied marsh currents and tidal sloughs and elevations of the bed, and he's the one that came up with that 1.9 billion cubic yards of sedimentation. Well, that filled it, because it filled it very suddenly, filled these bays very suddenly, the deposits never consolidated. And in fact, there are lots of places in these marsh areas along the shore where there's 80 feet of mud, that was filled in during that time. And if you put a surcharge of a few feet of earth on top, of soil on top, you'll find that it starts to consolidate. There's a housing development here in Corte Madera where during a spring tide, exceptional tides, there's salt water in the backyard because the people's houses were built on fill that was put on this deep deposits of mud. So if you go out in San Pablo Bay in a boat with a 20-foot length of 1-inch pipe, say, as we did to put markers out there, if you stand on the boat and push the pipe into the mud, there's a little resistance at first, and then just goes out of sight practically. There's just no strength to that mud. So the answer to your question is, Andy, you'd sink pretty far if if it weren't for that crust in the bed. Well, the supply of sediment had a profound effect on the San Francisco Bay system, and I'll try to sum it up in a couple of minutes. Well, I'll tell you what. Let's do this on Tuesday next. There's quite a bit to go. So I'll meet you all on Tuesday.